हेलो। गुड मॉर्निंग सर। मेरी आवाज़ आ रही है? ओके ओके। श्योर श्योर। ओके। Sure, sure. Uh, my screen is visible, right? Uh, my screen is. Oh, sorry. Yeah, yeah. My screen is visible, right? And the PPT and this also. Okay, okay. Uh, ठीक है. Thank you. Before I start, I just wanted to ask whether anyone has any doubts in the last two lectures which we covered related to random forests, k nearest neighbors, and maybe the linear classifiers if you had a look after the session. So if you have any doubts in assignments or something like that, because I got a mail from some of you people telling that the notebooks are not working, that they are getting some sort of compilation errors. So is anyone else facing the same issue? Hello. Okay, so no one is replying. I think everyone is fine. Okay, and does any one of you have any doubts related to the last two sessions in either core part or the theoretical part which we covered? Okay, and what about the lecture part? The lecture part was clear, or do you have any other doubts? Okay, ठीक है. So then I'm starting with today's part. So before I start, I think this is going to be the last session which will conclude this MSML program. So you guys must have had amazing 4 days listening to a lot of people, and I think the other people have covered the part related to how do the models work, and they must have discussed various areas like computer vision and NLP and other part. So I hope that by now, at least what you know is that what a convolutional architecture is, and how do you actually write loss functions, and what it means to actually train and optimize your networks. And so basically, you must be knowing some part about backpropagation, and then you must have a definition of some tasks which we can perform in deep learning, like automatic document summarization or some sort of video generation. So last time what we talked about was image classification, and at that time we had discussed the k nearest neighbors and how k nearest neighbors actually is not a good classifier because it actually takes on time during the inference phase and only o1 time in the training phase. So then we had discussed that what we actually need is a classifier which can reverse these two things. And then we had discussed how representing your image in terms of weight multiplication by a matrix W reduces to a form of Wx, where the weight is actually denoting the individual template which your network is learning for a single class. So then I had shown it to you. So we were not able to discuss the theory and optimization part at that time. But what happened was that I showed you the big ideas, and what we saw was that when you are actually learning your hypothesis through linear classifier, in the end you are actually able to get an image for each of the 10 classes. So that was the point where our discussion had concluded. And today, what we are going to start with is what goes on inside a neural network. So I'm not going to discuss how the architectures are working. Rather, what we will do is we will just take one of the architecture and we will try to understand what is going on inside it. So yeah. So some of you might not know where the notebooks are. I think I sent a mail yesterday, and ma'am must have forwarded it. They are already in the notebooks, and lectures both are on the GitHub repo. Yeah. So yes, we can start now. So So I have discussed the basic thing which we did discussed till last time, and if you had gone home and actually run the notebook related to the linear classifier, you would have seen that in the end we were able to visualize the weights of individual categories. So here we have taken the example of a image here like a horse, where this represents a mean image for the horse class, and as you can see that this actually contains some sort of bobbish body and two heads. So one of them is looking towards left and one of them is looking towards right, and perhaps by looking at this image, what you can estimate is that when this network was subjected to the training process, it actually contained the images of the horse in both left and right orientations. So what you ultimately ended up with was the mean. And then we were able to actually discuss about how you can use only these 10 images to compare a new image and check to which of the categories it belongs to. So we had discussed how linear classifiers will actually give you these sort of 10 images, and then for each of new image which you get, you can actually apply the k nearest algorithm to only these 10 places, and this is better than the traditional KNN because what you're doing is only comparing the Euclidean norm with the 10 examples here. And so because these 10 is a fixed number, so your time is automatically going to be constant of order of 1. So once these all semantics are in place, actually it shows us two problems. So the first problem is that each of these image is very blurred. So automatically what we want is that can I learn something in my network which actually looks to be more perceptually clear and will help me to actually get a better shot at accuracy. So because when we saw the linear classifier, it was able to perform around 49% with a SVM loss, and your k nearest neighbor was only able to throttle till 28%. So our question for today is that can we do better? And if we can do better, then what are the technical aspects that we actually need to hammer upon? So uh, what we discussed till now was that there was only a single weight matrix W. So for each image pixel, you were only multiplying it by a single weight matrix, and the linear operation which we were considering till now was one of the most basic operations which comes to your mind, that you take a weight multiplied by each individual pixel and then automatically add it up. So then the next obvious way in which we can do better is actually to perform this multiplication steps many times. This is the first thing which I can think, that if you will go and want to do better than a linear classifier, in that case, if you want to do better, so then what will happen is that actually each of these layers will emulate the multiplication process. So it's like, suppose this layer is having weights W1, and this layer is having weights W2, and this layer is having weights W3. So what you are doing is actually you are passing your input here x, and then you are going for one of the linear classification which gives you w1x, and then this guy is going again to the second layer and you are computing a matrix product. So these are the final outputs. So this is the first intuitive thing which comes to our mind, that what you can do is actually cascade multiple layers of neurons together, and each of the layers in this is actually gonna represent one linear classification step. So our intuition is that if I can perform a linear classification once, and I can repeat that step twice or thrice or many times in form of cascaded layer, then I can actually come down towards learning a better feature representation, and these sort of blurry things which are appearing in the images might start to look a bit clearer when you go ahead and plot the individual weights in each of the layers. And the plotting part I explained the last time, that your weight matrix is actually having the same dimensions as your image. So once you are actually learning it, then you can just plot it again by reshaping the numpy array. So when you look at this sort of structure, and when you look at how it actually represents cascaded many steps of linear classification being performed on top of each other in different layers, turns out that this is not good. So why it is not good? First is that we came to linear classifier, then we built an intuition of why we can put it in forms of layers. But why it won't work is because consider that you are having a cat image and you are putting that guy in the first layer, which is marked here as green. So what will happen is that cat will be actually processed by all this stuff, and it will give you some random feature vector which will go and then be input to the second layer. So here what will happen is that all of the cat, so come to the blackboard one. So suppose I'm giving a cat to it. So what will happen is that this cat is containing some numbers, and here when you look at this image, you can actually understand in which region of the image actually the cat is present. But what happens is that when you perform the multiplication step of w into x, at that time you are unrolling your entire image in form of a single column vector, and then you are multiplying. So when I'm unrolling it in form of a vector, what I'm doing is actually I'm destroying the ordering of the pixels in this image. So this entire 2D image now becomes a 1D image, and then you are multiplying it by a weight matrix w. So ultimately what you are doing is actually you are destroying the XY structure in your image. But actually, once that structure is destroyed in this step, that then automatically whatever processing you will do will have the same limitations in the subsequent layers of containing weights W2 and W3. So actually what you need is a way in which you can actually have some sort of layer mechanism, and each of these layers is actually performing some sort of linear classification, but you are not destroying your image into some form of blind column vectors. What you need is a way to basically preserve the content of the image and actually understand and maintain the notions of xy regions of the image, so that what happens is that when you perform the learning step, in the first learning step you have an image containing a cat, and that cat can be present anywhere in any region of the image, and gradually as you parse this image through various layers of the network, you are actually able to zone in on exactly which region of the image contains the cat, and then you are able to solve some more interesting problems, which are not just that you tell me whether it is a cat or not. Actually, can you cut out the cat from the image or not? So such sort of problems cannot be solved if you take a sequence of these linear units arranged in such layers, because what you are doing is at the input you are actually cutting off and not preserving the xy nature of the image. So this idea, so 2 points to take away from this was that you can take a linear classifier, and that linear classifier's concept can be put in layers, but keeping it as a sort of interconnected network of neurons won't work, because it is actually distorting the spatial structure of the image. The conclusion from this is that you need a way to actually take the same semantics but preserve the XY nature of the image. And this is the thought which actually gave the rise to convolutional neural networks of our cases. So in convolutional neural networks, I'm not going to go much into the architecture because I think this is clear to you. But in convolutional architecture, what makes it different from this guy is that these two things are performing same operations, but a convolutional network is actually able to go ahead and preserve the height and width of the image. So as your image is going downstream, its depth is gonna increase, but its height and width are going to decrease. So what you can go do is actually when you are passing an image through a convet, you can actually track which of the pixels is going inside the image, and then in that sense the XY position of the image is gonna be conserved. So think of it like this, that I have one layer, and then I am having another layer. And what I am doing is actually I am taking an image of 4 pixels. Let's say this pixel is 1, 5, 10, and 12. So what you are doing is that you're passing it through a max pool operation of a kernel size 2 cross 2. So what this thing is going to do is actually it will give you one number containing 12, right? Because you are taking a window size of 2 cross 2 and taking a max. So if you see this 12 number and you see that there was a kernel size 2 cross 2, then you can actually map this number back to these 4 parts. So even if these 4 numbers compress to one, you still know that this pixel is actually arranged, and it gave you 1 pixel. So in that sense, this image's spatial content was preserved, which would not have actually been performed while you were doing pure cascaded layers of linear classifiers in form of neurons. So these was the basic motivations behind ConNets, and how they are actually better than these layers of networks, because they're helping you to preserve the spatial content of the image. So before I proceed, do you guys understand what I was saying? Hello. Okay, very well. Uh, then let's talk a bit about what sort of computer vision tasks, what sort of computer vision things we can do. So, what are the various things which we can do through a computer and a network, and what are the differences between them? So, consider this central image. It contains a cat, and the first type of thing which we discussed is that I will give you this image, and you just have to give me a score, like maybe 50% or 80%, which tells me how confident you are that that how much degree of catness is present in this image. So you will take an image, and what you will do is you will output the scores corresponding to different classes, and then you will look ahead towards the cat class, and that will give you the confidence about the degree of catness present in that image. So this is the task which we have already discussed, which is basically related to image classification. Then we can go ahead and we can solve several of the vision related tasks. So one of the tasks is that you are given a cat, and what you want to learn is a bounding box which is denoted by red color, which can accurately surround this cat. So as you can see is that this bounding box contains a rectangle, and a rectangle can be defined in terms of height and width. So what this problem reduces is that what you want to learn is a rectangle's dimensions, which can accurately surround the cat in this image. So first you want to understand that this is image is a cat, and then once you have the cat with you, you actually want to put a bounding box around it. So you should know the exact locations where that red bounding box is going to be present. So this task is actually known as classification plus localization. Classification, because first you are searching for where the cat is, and the localization part is that you actually want to understand where in the object, where in the image should you draw the bounding box to surround the cat. Then what we can go ahead is look at this rectangle and say that I'm not satisfied too much, because this rectangle is actually containing the cat, but it is also capturing the region containing grass. And the reason for that is because the cat is not rectangular, but the polygon which we are trying to surround it with is a rectangle. So some of the space in this rectangle is going to be actually containing the very bad objects, like this grass, which is actually not a cat, but that was the original thing which we were trying to do. So then we can proceed towards a more challenging task of semantic segmentation, where instead of drawing a polygon, actually what you are doing is to try to classify each image, each pixel of the image, that to which category it belongs to. So here in this portion, I managed to actually look at the cat and mark each pixel of the image as a yellow, which denotes that this thing is actually gonna represent a cat. So here you can see that there are four different types of colors representing the sky, grass, cat, and then some sort of bush behind, which might represent a mountain in the pink color. So this is good, and once you have this image, what you can go do is go ahead and uh, uh, take this entire yellow region and then just output it in form of a cat which has been properly cut through the image. So for algorithms guys, this actually reduces to taking the cat and then starting from one pixel and then applying some sort of flood fill algorithm to it to actually isolate this yellow region from the entire image. Then what happens is that there are some more challenges which actually talk about instance segmentation, in which what happens is that you are given multiple instances of same category in the image. So till now in this part you were only having one cat, but suppose that you are trying to understand how many you are trying to understand how many people are there in an image, or how many dogs are there in an image. So let's say that you are going ahead and putting a CCTV camera at a metro and you want to track how the people are moving. So the first step in that is to actually look at a frame containing all the people in a crowd and to actually cut off each person and then understand how many people are there in the image. So in an image there can be 100 people. So as a whole people is one class, but there are 100 people, 100 entities of that class, because there are 100 people present in that image, and your task is actually to go ahead and to cut off each of the person present in the network. So in this case, like you can see that we managed to go ahead and cut off the red portion representing one dog and a green portion representing one dog. So if I rank these tasks in the increasing order of accuracy, the most easiest one is you just identify the cat in an image. Then slightly more difficult is you just regress a bounding box around it. And then you reduce the notion of bounding box to instead a pixel level classification to try to understand which region is actually representing which portion or which category, and what you end up with is a mask in form of a semantic segmentation map. And then a more challenging thing is that you actually want to detect instances of the same object belonging to same category. So at that time you can have two dogs in a picture, but what you want is the ability to color code them differently. So there is one dog which is red colored here, and the green dog which is separate, and you can see that there is a special boundary which the network has learned in between them, which actually allows it to separate the red region from the green region. If I had just gone ahead and only took the dog class as a single class, then what it would have done is that it would have combined all the dogs together to give a single red region, which would in fact have been a semantic segmentation. But this is the example of instance segmentation. So once we have all these things in place and we understand what are the tasks which we can perform in vision, and how complicated they are, we already know that there are several architectures for it. And then we can design our own loss functions which can actually work on these individual tasks. There is one thing which we don't know, which is that every all this magic is going to be happening through a convolutional neural network, but we don't know actually what is going on inside a network. So right now what we have is that if you remember our image classification part, you were just having some sort of magic thing going on, in which you were passing your input image, and in the output what you were having is the score of basically 10 categories. You were having 10 outputs in your numbers, and you were not talking about what was going on inside the network. You just knew that you were able to make this network do something when you were actually going ahead and train it with a classification loss or some sort of SVM loss at this classification layer. So it is possible that as an industry practitioner you can get your convolutional networks to work properly by just making a data set, devising a loss function, and then training it, and without taking care of actually what is going on inside a convolutional neural architecture. But generally, as researchers, and if some of you might be graduates and PhD people, you need to understand like what is going on inside a network better, so that you can take those insights and develop better layers which can help you to actually perform better on the tasks which you are targeting. So uh, yeah, so okay. So is this part clear? Like what are the different sort of things which you can perform with vision, and why is it necessary to actually visualize the internal mechanics of a network? You can just ping OK in the chat if it looks okay to you. And in case you have a doubt, uh, okay. Yeah, so this is looking okay. So you were able to understand what I am talking about? Uh, See, this is a interactive session, so you can reply and you can even show your webcams, because that way I will come to know that you are understanding. Uh, okay, uh, okay. So, and to other people, is the stuff which I talked about, that why do you need to visualize the things? Is that understandable? Okay, okay. So, till now, what I have talked about is that a convet, each layer of the convet is actually representing a separate linear classifier. So, you look at one of these layers, and this is actually performing the operation Wx, which reduces to your linear classification case. So it is intuitive that the way in which we actually went ahead and were able to visualize these individual images. What you can do is perform a similar step in a network like this. So what you have is that I have taken different architectures. So on the left, what you see is a LXNet followed by some ResNet and DenseNet variants, and I passed an image through the network, and then it went ahead and passed through several convolutional layers in the end, which you're performing classification. So this red guy shows you that you are going into a single layer, and that layer is performing the convolutional operation, and each convolutional step actually contains filters, and the filters are governed by parameters. So let's say that this LXNAT has a dimension of 64 cross 3 cross 11 cross 11. So this means that this guy is actually having 64 filters present at the first layer, and the spatial extent of each filter is 11 cross 11, and that filter is actually operating on the three dimensions of the image. So what you want is actually a way to plot these 64 filters. So what you can do is that this 3 cross 11 cross 11 is denoting a filter weight. You can just take this image and can plot it, and then since so each image will be a RGB image of 3 cross 11 cross 11, and then there are going to be 64 images out of it. So what you can have in front of you is a 8 cross 8 grid containing 64 images, where each image is actually representing what your filter has learned, because that 11 cross 11 cross 3 is getting unpacked and plotted here. So what I want you to observe here is that when you go ahead and look at the lower layers of the network, at that time you can see that it actually starts to learn some basic things related to like edges, circles, or basic, or maybe some sort of orientations of things. So you can see this guy, this represents that it is looking for some blob which represents some sort of green thing, and then this image is actually looking for all the edges which are tilted towards maybe right, and uh, then this thing is representing something which is tilted towards the left. So uh, when you are thinking at when you're trying to visualize the initial layers of the network, you start learning the basic things which make up the objects, which are the points and lines. But you still don't have a notion about what an entire object is. This is, but the important part here is that you can go ahead and visualize each image, and those activations will actually help you understand what sort of features is our network trying to learn. So uh, another thing which I want you to see is that if you look at these individual images, then as your network is becoming more complex, then the clarity of these images are becoming better. So you can look at this pink blob. So this pink blob here is something like very small, and by the end it came to densenet, it became bigger and slightly more clearer. So actually this illustrates visually that as you're making your architectures better, you are actually able to learn better templates in individual filters. So then what you can tell me that, okay, so I was able to go ahead and look at this individual red region representing the first filter of the connet, and I was able to visualize this thing. So can I actually understand what a per general layer, a layer which is slightly deeper inside the network, what sort of features it is trying to learn? So could I take the weights of those layers and then actually try to visualize those weights in a similar manner in which I am trying to actually visualize it? Turns out actually no, you can't do that, and there is a reason for that. Uh, so just a minute. Okay. So what you have in front of you is a demo which is running off the Carpathy's backend, and what it contains is a network which has been loaded inside the browser's JavaScript inside the browser and is being trained right now on my PC through my backend to my local PC. And I have gone ahead and loaded a network which can actually give me a 80% accuracy on CFR, and I am passing the images through this network in real time, and this graph is actually showing you how the training of this network is proceeding. And what we are trying to understand is basically we are taking the input image and passing it through several layers of the network, and for each of the layers I am trying to plot the individual features in form of such grids. So when so our intuition is that if I am going deeper, then the initial filters were trying which we visualized in this slide showed us some sort of edges. So as I go deeper, what I should actually see is some sort of things which can represent maybe complex structures like faces or something like that. So let me pause this guy, and yeah, let me pause it, and as you can see that while you are training, your loss is going down, which actually represents that your network is going to converge. And now let's look at the individual activation. So this was your first image in which you were taking your input image, and it looked input image was there, which maybe represents some sort of aeroplane if you look at it in between. And your layer actually when you are going through your first layer, at that time if you go ahead and you visualize the individual filters, because there are 16 filters at this layer, that is why there are 16 things here. And you can see that each of these things is learning something related to the aeroplane's boundary. And but there is a common thing in them, that you can actually see that it is trying to run one of the wings of the aeroplane, or maybe a particular edge. So right now your network is stuck at learning some of the edges of the aeroplane. But what happens if I am going deeper? So when I go deeper, I am not able to make out the aeroplane any longer. If I go deeper inside the network, then if I look at this layer, and this layer is actually containing 20 filters, and these 20 filters are being actually visualized in this individual thing. And if I zoom in on this individual filter, I can just see that what it is showing me are some patches, and there is no structure in these learned filters. And otherwise, what would have been what I was seeing in the initial network while I was trying to visualize the aeroplane. So why is it? Uh, the answer is very easy, that while you are going ahead and are let me come to the slide 3. So I have shown it to you that while you are trying to actually learn the network, at that time your initial layers are actually able to learn the edges, but when you look at the individual parts, that times when you look at deeper layers, that time the things start getting screwed up. So we need something better which can help us to visualize those lower things, and we need to understand like what is the problem going on. Why can't I use the same logic of visualizing the weights to learn to actually understand what the network is learning at deeper layers? Because all you saw here was these random blobs inside the figure. The idea is very similar, that when so the reason why the deeper layers of the network were not able to show the image is that at this point I was actually talking about individual images pixel, and at this point I was computing a function f of xy. So I was going ahead and computing how my weight is actually how the filters weight are actually varying if the pixels of the images are changing. So this logic was able to work for the first layer of the network. But what happened is that when I look at the second layer, at that time the filter of the second layer, which is this output, the fxy thing, is actually going to become an image for the second layer. Because at this time the image is input, but at this time in the second layer there is a different input to it. And when you're looking at this guy, that time you are not looking at this image, instead you are looking at this image. So that is why the image which you see in front of you is actually showing that how much is. So if I'm looking at a layer L, it is showing me how much the features in layer L minus 1 are being varied. It is not showing me how the features at the initial input are going to be varied. So that is why I am not seeing proper higher complex structures if I try to visualize the filters of the layer directly. So let's say that I'm looking at the fifth or seventh layer of the network. Uh, while I try to visualize the seventh layer's weights, that time I will only see that what does the output of the sixth layer look like, because sixth layer is going to be fed inside the seventh layer. So instead, what I want is a way to visualize this seventh layer weights on the basis of the initial input, which was passed as an image to the first layer. So this is something which we are striving for, that we want a way to actually visualize the deeper layers of our network. And right now it doesn't work because it just shows us the outputs of the previous layer, which is not representative of the coordinates input. So is this part clear, like why we are not able to visualize the weights, and what is the thing which we are striving for, what is our aim to do? We want a way to actually understand how the input features are there, how the input features will actually be visualized by the seventh layer. So this part is clear. Anyone else? Okay. Can you tell me what is not clear? I got a ping from Shanmuga. Uh, yeah, that it is clear only a little bit. So can you tell me the majority bit which is not clear? I will try to help you understand that bit better. Yeah, the real life application of this thing is neural style transfer, and neural style transfer actually comes from two parts, which talks about generating the content from internal features of the network and then generating textures inside the network. And I am telling you how visualizing actually helps you to proceed towards generalizing, towards learning from the content, and the towards actually learning how to extract the content and style features in the image, and then to make your image more colorful. So the way to actually understand this, so these are the motivations behind neural style transfer, and you can use these visualizations to construct better architectures, which will impact your real world better. So that is the thing. Okay, so this is the stuff which I talked about last time. So let me talk a bit about something more. So we have understood that what I actually want. Can you guys tell me like what is not clear, and maybe uh, I can help you out with that, because I don't. I think that there is still a bit of doubt in your minds, like you are not clear with the things. Yeah. Good morning. I have done that. I have done. Yeah, yeah. So I have done that. I have went ahead and I have prepared this thing for you, which will allow you to actually visualize the individual activations of the figures. So right now at this time only, I am going to explain one concept and I will show it to you guys in code. So yeah. So that will take care of the part which tells you that you are not able to actually think of how to implement it. Yeah, yeah. Yeah, sure. Okay, okay. So first I am going to explain what it is creating, and then I am going to run the notebook which will tell you how it is creating. Okay. So the how part, that you are not able to understand what it is creating, and how it is creating is that clear. I will go into the method to do that right now. But yeah, okay. So, what we found was that if I take an image inside my convolutional network and I try to visualize the individual filters of the deeper layers, then what happens is that I end up with this garbage which you can see in front of you. This garbage cannot be used to learn anything, to understand up anything of what our network is trying to learn, and it only makes sense at the individual layer of the network, where it actually tells us that okay, that I'm learning some sort of edges. So we need a way to actually try to make sense of what the network is trying to learn at the deeper layers of the network. So what can be the first intuition which we have? So in my initial lecture, I had told one part that while you are having a neural network, at that time, each of your neurons is going to fire and it's going to give you some sort of number, and that number is actually representing the pattern of activation inside the neural net. So what we can go ahead and do is that we can look at individual neuron in each of the layers and try to actually plot whether that neuron fired or not when my image was passed to the network. So uh, maybe that can give us some sense about how the things are going and what sort of things are we trying to learn. So let's suppose that what is the thing which I can think for visualizing this is that I have one layer here and I have second layer here and I have third layer here, and maybe this guy is containing 4 neurons, and I am having a filter here which represents my convolutional layers filter. And what I'm doing is I'm going ahead and passing this image inside this filter, inside this layer, and this image is going to become a bit smaller, and then it's going to become even more smaller but more deeper here. And I'm trying to look at how much was the activation, or whether this neuron fired for this particular image or not. And when I try to plot that, then what I when I try to plot that in form of a figure, actually I will come to know whether the network is learning something or not. In this part, in this figure, what you see in front of you is that the image of a person, maybe this figure was passed through a network, and you can see the through a LXNet architecture, and on the top you are able to see the individual layers, and each of the columns is actually illustrating the neurons at that layer, and each of the image in this is telling you how much it activated for a particular input. That is the scenario. And when you go ahead and when you start visualizing the deeper layers like this con3, at that time you can see that a particular neuron is actually showing you some sort of white blob, which represents the region of the person's face. So this tells you that okay, that we are on the correct path, that by visualizing the feature outputs of this particular neuron, I can actually plot some sort of diagrams, which gives me information about how much about how that this region of the neuron is sensitive towards this person. So it saw this face, and then when I tried to visualize it, it showed me this white blob in between. So yeah, so by looking at individual activations, you can actually isolate the exact regions of the image where your neuron is going to activate, and that is going to give you a sense of the representation which your network is trying to learn at the deeper layers of the network. So once that thing is clear, then what we want is that okay, so what you got now was that just a minute. Yeah. So is this part clear that when you look at the individual feature map of a neuron, that time you are actually able to understand that which region of the image it is sensitive to, and when you have that, then you can get a deeper sense of understanding what that neuron is trying to actually learn. So yeah. So more formally, it's like if you look at the fifth layer of your network, it contains a 128 cross 13 cross 13 size feature map, which is actually the output of that network. And you can go ahead and you can visualize each of these 13 cross 13 image, and that image you can threshold to a grayscale value, and you can look at all the things which lie above the thresholding value, and those sort of white blobs will tell you which region of the network is actually being activated the best. So by looking at this, you come to get a sense of the higher activations or higher structures inside the image, which the network is trying to learn. So is this part clear that you can visualize the individual activations of each of the layer, and actually show it as a individual grayscale image inside the network? Uh, I had one doubt that at initial level you fix 64 size. Is it constant for each image? Yes, it is constant for a particular architecture, because a particular architecture always contains fixed number of channel to be given as input. but you can give a random sized image to it as long as your network doesn't contain fully connected layers. So that is why a single connect can actually help you to perform multi-scale inference during the testing time. So it is not required to keep a fixed size image, but yes, the number of filters should agree in the coordinate dimensions. Yeah. Okay. So I'm not. Yeah. Please tell me. Can you talk about a particular example? Can you give me a question like what sort of application you are trying to make a architecture for? Okay, the thumb rule for so there are two parts. One is that as a researcher, you want to know what sort of things you can do to make the performance on a particular task better. And then there is another dimension in which you are not a researcher, you as a person are in industry, and you want to choose which of the architecture you want to use in your problem. So, is your question related to first category or second category? Okay. So for first one, what I generally do is that I go to papers with code, and there I look at the things by their application. So I go to papers with code, and then I go to browse state of the art, and at that time, what happens is that at that time I can see which of the applications I want. So let's say that I'm going in the vision part, and what I'm trying to do is some sort of image classification thing. And then if I'm a researcher, then obviously I have some sort of data sets with me on which I need to perform best. So I will open up this dataset guy, and here what you can see is that each of the best models has been ranked according to their performance on this dataset. So I will go ahead and read this paper, and its code is also available online. So then I can use up this model directly and rest assured that it is one of the best of its own kind. So that is the pipeline which I typically use. Okay, yeah. Till now, what we have done is that we were trying to visualize what our network is trying to learn, and we started with our initial layer, and we saw that it was able to learn the edges if we were trying to visualize the individual weights of our convolutional filters. But when we went deeper inside the network, we saw that just visualizing the weights of the filters gives us garbage, and what we wanted to have was a better way to visualize the deeper layers of the network. So our intuition was that if my network is actually consisting of a lot of neurons, and if I'm able to understand which particular neuron is firing for which of the images region, then I can actually understand what my network is trying to learn. So what I went ahead was take an image and pass that image through my convolutional network, and then for a particular layer, I look at the layer's output, and that output will actually contain uh, different height cross with image for containing different filter dimensions, and I can strip off one of the filters and I can plot that image. So here the convolutional layer's fifth output was a 128 cross 13 cross 13 output, and I can break it down into 128 13 cross 13 images, and that images are going to contain some random numbers, and I will then threshold those numbers and put them into and then transmit or basically project them to a grayscale dimension of 0 or 1. And in the end, what I will end up with is a grayscale image in which the white region is actually telling me how much this network is activating for a particular image input. So when I pass this person's figure through the network, that time I was able to see that it was activating slightly at this white region, which showed me that this particular image was actually, this particular filter was actually sensitive towards that person's faces. Okay, so in the figure you see each of the columns is actually representing the outputs of different layers, and if I look at one column, then each of the rows in this column, each of the, so if I am looking at con 5 column or maybe con 3 column, then all the things which lie in this column are actually the 13 cross 13 visualizations of 128 filters which were present at that layer. So then uh, there is one other thing which we are not able to understand right now. It is this, that right now what happened is that I am taking a person's face and I am passing that face through my entire network and getting which of the regions does that network uh, activate at. So how do I uh, identify the exact region in an image where a network is starting to look? So let me try to make this thing a bit more clear. So I will take an example about how a general convolutional neural network works. Yeah. So let's say that what you are doing is basically trying to classify the image of a cat inside your network. And what will happen is that you have these multiple layers through which you are trying to pass this image. So you pass this image through here, and then you're getting some sort of outputs, and what you see is that those outputs are actually getting activated for a much larger region, like this whole guy, which represents that okay, it has started looking at this region to basically search for the cat. And then as the network gradually goes deeper, then this green blob will start becoming a bit smaller, and it will actually start coming around the boundary of the cat, which will help the network to exactly understand in which region the cat is present. So this green blob is going to become smaller as you are going inside the network, and ultimately it will converge more or less to the cat's boundary, at which time the network actually learns that okay, that now I am a bit confident in which region of the image I need to look to understand what is the cat. And once this region of green blob is becoming smaller, then finally you are able to take this image and then output a classification score representing how good your cat is looking. uh, so once this part is done, then what you can do is actually take a look at this blob and isolate the exact region where this cat is there. So this is what is going on inside this neural network, and what I actually want is a way to see these green patches which are gradually being refined towards the cat boundary, and helps to understand the exact region in the image where the cat is there. So this a network is able to do by itself, and in the end it is actually looking at this green region and then outputting a score that it is confident that this is the cat. So what I want is a way to look at this exact region. I'm trying to answer the question that which is the region of a particular image at which my network is currently looking, to try to understand where a cat is present. So the best thing which I can do is basically uh, I can take this guy which represents a animal or this elephant, and I can cut this elephant into smaller pieces. So let's say that I am having this image and I cut this image into four parts. And then what will happen is that if I cut this image into four parts, so let's say that one of the part contains left eye of the elephant, and I pass that left eye through my convolutional network, and I plot these same activation plots for each of the layers. So what I will actually find is that my network is actually currently activating, some neurons in my network are being activated best for the eye of the elephant. So the idea is simple, that your network contains a lot of neurons, and you want to understand what sort of features does each of the neuron learn. Okay, so the way you have to, you can actually understand that which neuron is activating best by actually going ahead and plotting this grayscale plots of each of the filters. So now what you are trying to answer is the question that which of the neurons in my networks are more sensitive towards the elephant's eye, or which of the neurons are actually trying to understand, which of the neurons in my networks actually look at the to the at the elephant's ears, or which of the neurons are actually looking at the elephant's feet. So the best way which I can do it is actually take a elephant, and I can cut its ears and cut its legs and cut its tusk, and then I can pass that individual cropped image to the network, and I can see that which of the neurons are activating the most. So if I passed in the eye and I saw that this neuron has actually activated for the eye portion, then I come to know that this neuron is actually sensitive towards one of the elements of the image. So uh, this is the way in which actually random cropping along with the plotting of activation maps can help us to understand which aspect of the image is a particular neuron of the network sensitive to. So uh, this is like the most intuitive idea to answer this question. And what you see in on the top in the first row, so this is like showing you some of the eyes or some sort of ovals of the elephant's eyes. So what we did is actually cut off the eyes of many elephants, and then we passed these eyes through the network, and we checked that okay, a particular neuron was activating for each of these eyes, and we were able to conclude properly that okay, then this is the case that this neuron is actually starting to learn the activations, learn the patterns corresponding to an elephant's eye. So yeah, so this is the way. So earlier, what was the problem, that while you were trying to actually visualize a individual neuron, you try to visualize its weights, but that was giving you garbage, right? So then I actually went away from the notion of visualizing weights towards visualizing the individual feature maps, and that feature maps activation gave me helped me understand how much does a neuron activate to in given input. And then I took the input and I partitioned it into various smaller parts which I can understand. So I as a user can actually partition the image of an elephant into the thing containing the eye, and once I was able to know that this is the eye, I passed it through the network and I got the activation maps. So the activation which was maximum corresponding to that eye actually helped me to understand which of the neurons inside the network uh, responds best to the eye. And in that way, inside my network, I was actually able to isolate the individual neurons which work best towards an eye, or let's say a text, or maybe some sort of edges. So uh, once these things start becoming clear, we have a way of actually understanding the features which a deeper neuron is trying to learn. And this is actually a bit better than just blindly visualizing the weights of the network. So is this part clear, that how visualizing weights and then visualizing the activation maps and finally cutting the input into different parts and then passing it through the network is better, and how we are actually able to identify the patterns which a particular neuron in a deeper layer is trying to visualize. Hello. Hello. Uh, yeah. Yes. Okay. I was not able to get the last part. Is there any analogy? Yes. There is a multi-resolution analysis which is if I'm not wrong, is your question related to that if I take different size of my image, then will it change the answer of which neurons is the network activating? So if I'm looking at a smaller eye, will and a particular neuron is activating for that eye, and if I start looking at a bigger eye, then will the neuron which corresponds to that actually change or not? Is that your question? Actually, practically it does. Theoretically, it shouldn't. Uh, that is because what you want your network is to be scale invariant. I don't want it to actually understand. I want it to understand that all the eyes are same, irrespective of how big they are. Uh, but actually, that is not the case because when you try to look at the object from very far, so let's say that you have a cat in your image which is at very far away, and you have a cat in front of you which is very close, and you are actually evaluating the network's prediction, how much degree of cat it is. So if it is close, it will tell you, okay, that I am 99% confident that it is a cat. But when you look below, when you look further away, that at that time your network's confidence will drop. It will tell me that I'm only zero point 0.4 confident. So this actually helps you understand that the network is not able to learn the classification in case the objects are very far. So at that time, if the scale is there in the image, that time the activations which the network is activating are a bit lower as compared to if it is closer to the image. So this problem is still there in the networks and they can't handle it. But if you can design some sort of loss which handles this aspect and actually makes the activations to be similar together, then it will be a good thing. But as per my knowledge, we have not been able to build the rotational and scale invariance yet into our convolutional networks. Okay, so you can do one experiment. You can take a image, compute its statistical coefficients, which are invariant to the features, and then you can pass it to the network. That will guarantee that it actually sees the things together. Okay, yeah. So looking at these patches of the images and then understanding which images region corresponds to which neuron in the deeper layer is being activated. This part is clear, right? Now I will explain how the neurons are, how you can why this approach of actually taking patches is bad, and a general way to actually visualize each layer's neuron by using gradient descent. And then I will go ahead and I will show you the exact map which will tell you how a neuron is being activated. So it's like yeah. So okay. So can I proceed, or do you have any doubts till the part which we have covered now? Yeah, ma'am. Uh, Ma'am, I'm not able to understand what you are trying to say. Yes. Yeah, 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 yeah. Yeah. See, once your network is fixed, you can't change it, right? See, the layer you are fixing, the layer size is fixed, and what I drew in this green blob was actually the activation, not the. It was the output of the layer. So that activations amount will automatically change. So each of this activation can be same sized, but if you plot those activations, so maybe each of these is a 28 cross 28 image, but in that image maybe the first blob from the left is a region of 4 cross 4, and maybe in the next one it's 3 cross 3, and in the right one it's 2 cross 2. So that is the refinement which a network automatically does. Okay. uh, yeah. So anyone else? Means I want you to make this thing clear that you can cut your image into parts, and that thing, and then you can plot the pass that part through the convolutional net, and you can plot the individual activations to get a hang of which neuron is sensitive to that part, and that part can be eye of an elephant. uh, okay. So the books and all this part, I have already shared with you in yesterday's mail. You can listen to this, and you can practice with that notebook. That is the thing. And for books, Partha sir has already told the books that day during the session. Bishop and something related to for CNNs, you can look at CS231N course, which I sent in the initial mail on day one. So that is the thing. Okay. So right now, our problem had been that visualizing the weights of individual layers was not good, because that gave you the crap and all that garbage which we saw on the CIFAR demo which I showed to you guys. Then we talked about partitioning your image into pieces and then visualizing individual activation maps. But there is still a problem in this. The first problem is that, let's say I am giving you an elephant, okay, and I want to learn how the network actually sees this elephant. So I tell it that, okay, you can cut it into eyes, you can cut it into tusk, you can cut it into legs. So to make this logic, I will have to actually perform my own effort, because I will have to go ahead and cut the eyes from this image, I will have to go ahead and cut the legs from this image, to actually understand what the network is visualizing. So, and there can be like many things. Maybe the network is just looking at an elephant's boundary, or maybe it is just looking at all the parts of the elephant which are very thick. So his tusk is also, his sound is also thick, and his legs are also thick. So that time it might be looking both at his trumpet and its legs. So there are like infinite combinations of things which hold some logic, and you can't actually go every time and cut that those things into patches to pass through the network to understand what a particular neuron is trying to do. So, although this approach of cutting the patches of the image based on our logic that I will cut off the eye of the elephant and then pass it to the network looks good, but you cannot compute such patches every time. So, what you want is a better way to actually find. Uh, you actually want a better way to understand that which of the images region is the network looking at. So let's say that I am giving you the image of a dog, okay. So this is the dog, and what I want is to understand that for this dog image, uh, which of the region in this image, at which of the pixels of this image, a particular neuron of my network is looking at. And I want to actually do this for I actually want to do this for all the neurons in my network, and obviously I can't crop this image into many parts every time, because uh, because it will become too complex. So an alternate idea is to actually what we can do is that we can take this image, and let's say that I pass this, I have already trained a network on the image classification task, and now I want to visualize which region of the image is the network looking at. So what I will do is that through this trained network I will pass this cat, okay, I will pass this dog, and a particular neuron will actually give me some output, right? So let's say maybe we are just looking at the output, okay, let's say that I passed this dog through the network and it told me that I am 80% dog, okay. And let's say that I cut off one of the regions of this image, and I pass it through this network again. Then what will happen is that the dog in that score will go down. So let's say that our intuition right now is something like this, that I want to identify the exact region in the image which my network is looking at. So what I can do is I can take an image and I can take a dog, and let's say that I pass it through a network and my network tells me that I am 80% dog, okay. And in the next step what I can do is I can remove the dog's head, I can remove or cut off the dog's head, and I can go ahead and pass it again through the network, and let's say that its confidence drops to 70%. So actually, since its confidence drops, then we come to know that the pixel which we had deleted was actually very better for the classification part. So if we find a way that we can mask the individual pixels of the image, and then by looking at the drop in the classification score, we can actually understand how important that pixel is. So let's say that this dog was standing inside in the was standing in the edges of a mountain or near a grass. So if I take this grass and if I delete this grass from the image, then let's say maybe the from 80% accuracy my confidence increases to 90%. So at that time I will come to know that the grass feature was in fact hindering the network's accuracy to accurately classify the dog. So theoretically what is possible is that I can take each pixel of the image and I can delete that pixel and pass that image every time through the network, and I can look at the classification scores. In case those scores drop, I will come to know that the pixel is bad for me, and in case they improve, then I come to know that actually it will promote the classification inside the network. So let's say that this dog had been of the size 128 cross 128. So instead of cutting this image into many parts, I would pass this image through the network 128 cross 128 times, and I will compute this sort of importance, like how much drop in the accuracy was there with respect to the initial image every time. So if I go and I predict this mask, then I will actually know which region of the image was actually important for the network by looking at the output of the network. So you pass the dog, you looked at the classification score, and then when you looked at the classification score, you saw the drop, and the drop is actually indicator of what how much important a particular pixel is. So then you can only take the pixels which actually improve the scores or only let's say drop the score by only 1%, and you can show those pixels in form of a map, and that map will help you understand which region of the image is a network looking at. So the main point to take from here is that you can observe the drop in the scores by actually masking some region of the image. And this is only done once you have trained your entire network on image classification part. So it's something like this, that I took a dog and I passed it through the network, and then I computed this step for each of the pixels. And when I computed this step, actually what I got was some of this yellowish blob, this white and black blob, which actually represents to me that this portion of the image is where I am looking at. So you can take this mask, and actually this white region is helping you understand which region of the image is your network looking at by going ahead with this drop in accuracy way. So is this part clear? Like how I can leverage the uh, drop in the accuracy levels to understand which region of the image is the network looking at. You can, if in case you have any doubt, you can unmute it. But I would request you to be a bit quicker in your responses because I can't wait for 5 minutes every time I'm asking a question. Okay. Uh, and to all the other people, because I'm only getting responses from, okay. I'm only getting responses from Shanmuga ma'am, Mustafa sir, and Gutu ma'am. Mr. Gutu, Gutu and Mustafa and Shanmuga are only responding. Only 4 or 5 people are responding. Others are not responding. Then there is no way for me to know. Okay. So our idea is very simple. I take my image and for each of the pixels, I actually pass it through the network and then I compute the drop in accuracy and I make a map out of it. So if this image of the dog had been of size 128 cross 128, then I would have passed this image through the network 128 cross 128 times to compute this black and white map. So if you pass it through this like this, it's 128 cross 128, which is still a very big number because 128 cross 128 is gonna be like in lakhs, and this is being this lakhs forward passes are being done for one image to compute this black and white saliency map. So what we need actually is to optimize it further. So can I pass my image only once and compute this black and white figure? Uh, this is the biggest question which I can have. Turns out, yes, you can do it because that is what the gradient is. What you do in a gradient in backpropagation is that you take an input and you compute how much that input is actually affecting uh, your change in the output. So in your case, your loss function is going to be what is the difference between the classification scores you are getting, and then you are going to start from that loss, and then you are going to back propagate through the network, and you are going to find how much the back propagation is impacting the pixel values of the individual image pixels. So you pass the image through your network once, you get a score, and you already know what is the score for the correct image, and then you find the gradient of that score with respect to the image pixels, and in the end you come back and you take that gradient map and threshold it, and what you get is the black and white portion of the image. So if you know what backpropagation is, then you know that you don't need to perform 128 cross 128 forward passes through this network. Instead, you can just do one backward pass, which contains a gradient calculation for how much does the dog score change based on the variations in the individual pixels of the image. So this is the idea. Now the idea is very simple, that to compute this black and white portion, what I can do is that I can go ahead and take my image and I can pass it to the network, and once I have some scores out of it, I can take the gradient of that scores and with respect to the image pixels, and what it will help me to understand is that what is the gradient of each pixel of the image with respect to the dog score, and I can actually take those pixels and then compute and then can compute the individual mask like this saliency map in a order of one. So once this part is clear, I can actually go ahead and implement it. So this is the part which I've actually done. Yeah, so let me run it and show it to you people. It's only 4 lines of code to understand which portion of the image is a network looking at. So the first part is very clear that for understanding this part, what I need is a network which has already been trained to actually look at a dog and give it a classification score. So all this. So first, we need a network which can actually go ahead and look at the individual classification scores, individual images, and output the classification scores. So this is what we are doing right now. What I did is I implemented this in the notebook, and I am going to show to you that how you can visualize the individual regions of the image in order of one, which a network is looking at. So first you start by actually taking some of the plots in input. So these all are, I'm using the PyTorch framework in order to actually um, process, and this is a network library which will help you to process the incoming images through a convolutional architecture. So I have imported some things, and the architecture which I am going to be using for a pre-trained model of classification is SqueezeNet. As you may know that whenever you are performing classification, first you are given an input image, and you need to actually normalize that input image. So that input image contains pixels in range 0 to 256. So you need to actually normalize those the pixels of that input image to lie in a particular range, and then you pass it to the network. So the way to normalize it is by computing is by actually subtracting some mean and dividing by some standard deviation the pixels of each image. And so the architecture which we are using is SqueezeNet today, and these are the means and standard deviations which it had used at the time of training to actually train each image. So these are the same means and deviation which we will have to compute at the inference time. So in easier terms, you have architecture SqueezeNet, which you have trained previously, and now you are having some evaluation phase in which you are passing an image and trying to understand that for the individual neuron, which of the particular region of the image is it looking at. So these are all the pre-processing functions which are not important. What is important starts from here. So PyTorch already has some models which have been pre-trained for classification, and this model will actually allow you to take a model from their pre-trained repo, and then since your network has already been trained, you don't want to actually train the network because you just want to visualize the things. So that is why you are going through each of the network parameters, and you're telling it that I don't need to perform any gradient during the backward pass because the network is not to be trained. We just need the gradients of the change in the dog score with respect to input pixels, but not change the weights of the network. That is why you are freezing the layers of the network right now during the inference phase. Uh, okay. So once this is done, you have a network with you which has actually been trained on your classification data set. You can go ahead and you can print this model. So you can see that this model is actually starting off with a corn layer, and then it's containing several units called squeeze and excitation units, and which are the convolutional layers. And as you are going below, the number of filters in your network are actually increasing from 32 to 48, and then sorry, the number of filters are increasing from 256 to 384, and then 512. So as you are going deeper, your network is becoming more thicker in terms of filters, and the outputs of the image will actually decrease. And finally what happens is, in a convolutional architecture, you are having a classifier in which you are applying adaptive average pooling. So it's like in this figure which I made here. that you are making your network a bit thicker, and the height and width of the images is decreasing. And in finally at the top what you have is a classifier which has been attached to actually compute the classification scores. So you can see that this architecture is following a similar pattern. We have gotten a network which has been pre-trained on ImageNet, and it contains weights where it was able to achieve better accuracy. And now our task is actually to look at some images in this data set and try to understand that for each image, which of the region in this image is a particular neuron looking at. So the model was loaded, but what we need is now some images which we can start looking through this model. So this will actually help you to look at some of the images. uh, yeah, so these all are nothing. This is just loading the image from the data set and plotting those images. So you can see here that what I did is I actually went ahead and I took the ImageNet dataset and I took some images, and there are around 5 images here which I can visualize. It contains maybe this dog and then some sort of grass and some sort of bears, and I want to actually now pass these bears through the network and to understand and isolate which of the individual regions is my neuron looking at. So what I will do is I will now start passing it to the network. So let me go ahead and run it for you people once. Then I will go and explain it. I will go in a bottom top down manner. Yeah. Okay, we are good to go. So what you can see is that what I first did was that I went in my data set and I computed my individual images, and the X represents a NumPy array which contains my image, and my Y actually represents the label of my image. And if I print the shape of this, what I see is that it is an image. The X contains 5 images, and each of these is having height and width of 22, 20, 224, and it is a RGB image containing 3 channels. So right now we have 5 images with us, which we are plotting, and in fact you can look at the individual categories of these images, and these categories are some numbers which are part of the categories in the ImageNet dataset. So once we have this with us, now what we do is that we have to compute this figure for it, which represents the saliency map. Uh, we have to compute this figure for it. So for that, I am calling a saliency map function. I'm actually calling a saliency map function for this image and for this guy which represents the label, because here what happened is that I was passing an image and I was looking at the dog scores to compute this image. So what I need is a function which can take in this image and tell the network to actually look at the dog category scores, and then it looks at the dog category scores and it helps me to make this figure. So it takes 2 arguments. The first one is the dog's image, and the second is that you need to actually look at the differences in the dog scores. So the image and the dog label are actually passed as input to the show saliency maps function, and this show saliency maps function has been implemented here. This is not doing anything. This extensor, so these are just pre-processing, because you have to actually prepare this image before passing it into the network. So I told before that what you do is you make for each of these image pixels, you subtract from it the mean and then divide it by the standard deviation. So this is what it is doing, and this preprocess function has been implemented. This is not important, but the important point is that you're pre-processing your image before passing it through the convolutional network, which in our case is a SqueezeNet. Then you are actually going ahead and computing the saliency map. So saliency map is going to be is this black and white figure which is going to be computed from this image and the label, and it actually needs a model to perform the forward pass. So that is why it is containing these three arguments. And if I'm going and implementing the saliency map function, then what you can do is it's very simple. Uh, just a minute. Yeah. So the idea which we had discussed was this, that you take your dog image and you consider one pixel of this dog image, and you change the value of one of the pixel, and you check how much is the change, how much change is there in the dog score. And by looking at the direction of the change, you will actually come to know that which of the pixel is more important. So basically what I want is to compute a gradient map for the individual image pixels. So that is why the image input which I was taking, I tell the network that you need to perform a gradient on this image, because what I want is I want that from this dog image I will change one of the pixel, and that change will actually produce some change in the dog score. So how this change map is actually going for each of the pixel of the image, that is the same thing as this map which is computed. So you take one pixel, change it, and this step is repeated for all pixels, which is giving us this map. So this is the change map for each of the pixels. So so what will happen is that I will take this input image, and I will compute the gradient of this input image, and this gradient is actually going to be the answer which we are looking for. This is what we are telling it, that you look at, so you take the input image, and then you pass that input image through the model. What you have with you is the scores of the ImageNet containing 10 classes, 1,000 classes. So like dog, there will be cat, brush, bush, something like that. There will be 1,000 scores, but you need to only look at the dog score from it, and you need to actually look at the change in that. So what you do is that you only look at the scores from those 1,000 categories which correspond to the dog, and then you gather those scores inside a numpy array. So here and then you are just performing a backward pass. So when you are performing a backward pass, at that time the change in the scores is actually giving you the gradient map of your input feature vector, and this gradient map will actually contain three dimensions of the image, because I told you that this was a RGB image, and the gradient map also contained three channels. What you will do is you need a black and white figure from it. So for each of the channels and containing the three pixels, you will maximize it. Then this guy is actually maximizing the three channel gradient map, and you are computing a black and white score. So let me run this algorithm once on the paper for you people, so that you can understand that what I'm talking about, and things just don't go on top of the head. Yeah. So what I have done is that I have taken my dog, and then I passed that dog through my network, and this actually spitted out 1,000 scores. So I only looked at the score which corresponds to the dog, and so this dog was an image. Let's say it contained 28 cross 28 cross 3 channels. So my gradient map is also going to contain the same thing, 28 cross 28 cross 3 channels, and I am computing this gradient for each of the pixels. So each location in this image contains three things. which computes the gradient across X, Y, and across RGB channels. So I'm taking this dog scores change, and then I'm making a backward pass through my model, and it's giving me this map. So this map has three channels, and I'm taking for each pixel the max out of these three things. And what I'm ending up with is a single map containing a 28 cross 28 black and white map, which looks like the dog in the picture. So this is the basic working of about how you can use a gradient to actually calculate the exact region inside the network where you are looking at. And as you can see that I have not done anything. It's just 5 lines of code which is giving you this black and this region of attention inside the network. So the gradient part is automatically calculated in the PyTorch, and you just need to give it an image and then compute the gradient and then take the maximum of that gradient in any direction. So that will actually help you to understand in that out of this dog, the network actually used this region of the image to classify it as a dog property. So yeah, is this part clear? How we computed the saliency map by taking the gradient and then back propagating it and then taking the max across RGB dimensions to get one saliency map. And this step can be actually repeated for each of the different categories at during the inference phase of our model. Uh, Anyone? So I'm waiting. Then we can proceed further. Hello. Okay. Yeah, I know everyone needs to practice at home. Uh, I hope this lecture will be recorded today and you can have a look at it later on. This is a lot of material to cover, but the basic concepts are almost same. So the idea has been simple that you take an image and you understand which region of the image the network was looking for while it was classifying, and perhaps that the way that network is able to converge that on that region will help us to develop a better application for it in the future. So uh, I showed you how gradients are computed using the backward pass. So that part should be clear. Uh, Perhaps you can, instead of typing, you can unmute your mic and speak because I have to read it otherwise. Anyone? Okay. Let me wrap up with the segmentation part. Okay. So then there is a idea which appears that if you look at this figure, what you can see is that when I computed the gradients in such way, I was actually able to understand the exact region of the image. So you can see that out of the entire image, it only took the dog here, and it actually went ahead and cut off the entire region containing this sort of uh, bars or windows at the dog's background, and this carpet is no longer there and this green carpet is not there. So it actually removed all the perturbations from the dog image, and in the end what you are having is just this orangish sort of map which is actually containing the dog. So can I use this image to actually now, if I take this image and I threshold it, I will actually have the exact pixels where the dog is there in the image. So now this is the beauty of this approach. That when I was training my network, actually I only told the network that this is the dog image and this is the label which tells you that okay, this image is that of a dog. I didn't tell it that this is the exact location where the dog was present, and it automatically was able to learn it while it was training on this classification task. So this is something which we get on the side, that by visualizing the individual attention maps of your network, you can in fact isolate the exact region or roughly the region where the dog is present. So in some sense, by taking this sort of saliency maps and then thresholding them, you can in fact compute the semantic segmentation maps for your image. And the power of your approach is that you only need to train your model on a classification task. You don't tell it the exact location where an object is present, and you just get some that as a byproduct on the site. So that is the importance of saliency map, and that is one of the best ways in which you can actually look at an image and then just compute where it is. You don't need a human to actually go ahead and annotate the exact location where the object is present. So this basic approach can actually be used in form of broad supervision, that you take an image, you ask a human that you just label it whether it's a dog or not, and my network will automatically learn the exact region where it is. Although this is good theoretically, uh, this won't give you the exact boundaries, but only a rough sense of where the object was present. So you need to still go ahead and actually it will not perform as good as the networks which are really trained on real labels of where the dog was there. But the aim of this exercise was to actually help you understand that a network in fact doesn't always need all the information which a human we think that it needs to be given during supervision. So some things it tries to learn on its own, and it can actually be used to reduce the human annotation effort during the dataset labeling. So yeah, so it's around 12 right now. Yeah, so I'm going to pause for a moment before I start further, because I will only explain further if you guys are feeling like it. Otherwise, I will share the PPT and all other part with you. So I'm pausing for a moment, and if you have any doubts for today or any of the last two lectures, you can let me know. Yeah, ma'am. Ma'am, I'm not able to understand your question. Can you please repeat? Uh, which image? Yes, it can. Okay, okay. No, it cannot. That is a good question. Uh, so what you are talking about is like suppose your image is containing both dog and a cow, okay, and yeah, and you are having two categories related to whether it is a dog or a cow, right? But what will happen is that you will have to actually choose between one. So either the confidence of both will be same, or it will tell you that it's a more dog as compared to a cow. So you don't have a way to perform a classification on more than classification for more than one categories in a single image. Okay, but there are some models which will help you to predict multiple categories in an image, and you can use the same concept of their category changes to actually form the saliency map containing both elements. But there will be a problem in that. The problem is that in this guy, what I had was a orangish color dog, right? But in your case, what you will get is a orangish colored dog and a orangish colored cow, and those will actually mix together. So you need a way to separate the dog with the cow, and you won't be able to look at it and just separate it. Yeah, yeah. No, no. See, let me go back to my this slide. So I had told this thing, right? That once you have something with you, you can compute its individual pixels in this instance segmentation thing, right? So you will get something like this, in which instead of this green and red region, the red might be the cow and the green might be the dog, right? And but the color of both will be orange, and you won't be able to learn this boundary which is actually separating the red thing from the green thing, because it's actually mixed together in a saliency map. You're just computing the gradient, right? So that is why saliency maps are like a simplification of semantic segmentation, and in fact, they cannot be used to perform instance segmentation. Yeah. Uh, uh, Ma'am, I'm not able to get your question. Can you please repeat? So that is what I told you, that you didn't label, and in fact, you were able to get the exact location where the dog is looking at, right? Uh, where in the network the dog is there. So this is like a byproduct. So you don't need a label for it. You don't need to tell it where in the image the dog is exactly present. But this is not that much good. You don't have the precise boundary of the dog. You just have some random dots. So what you can do is you can use this image as an input to an existing segmentation model, and you can in fact improve its performance. So in existing semantic segmentation model, you can take the RGB image and you can put this saliency map as the fourth channel, which will actually tell the network that you need to look at the region of higher activations. So that will be actually helping the network to aggregate and perform better feature selection to actually boost the classification scores, and that will actually improve your segmentation score. You got it, or should I show it with a figure? What I'm talking about? Should I show it with a figure? What you are talking about? What I am talking about? Okay, okay, sure. So see, what I'm talking about is that there are two networks which you are talking about. So just a minute. Yeah. So there is one guy which is called image classification, right? To this, you are giving a dog and you are telling that it is a dog and you are training it, right? And then there is another network. This is network one. There is another network which can take a dog, but you need to tell it where is the dog, and you train it. So this is segmentation model, and this is the classification model. Uh, just a moment. Yeah. So what I am saying is that what in fact you can do is, from this classification model you compute a saliency map. So this saliency map represents that region, that rough region where the dog was there, and you can give this saliency map as an input along with the dog image, and you can improve the accuracy of this guy. This is what I am saying. So your pipeline will actually contain classification with segmentation, and it will actually improve the score as compared to existing segmentation model. So yeah, yeah. So you need to concatenate it with the channel dimension. So we are left with one part, which was related to neural style transfer. Uh, in fact, that is a bit easier on the end. I will just show its output to you, like what all we can do. So it's like I have one girl and I want to paint her picture in terms of the painting by Vincent van Gogh, A Starry Night. So this is the sort of processing which I can actually do, and I ran some gradient descent on it, and you can see that the girl is actually coming out in the style of how Vincent must have painted the painting. So this is the power that in fact you don't need people to create your portraits or paint your portraits. All those sort of artistic things can be in fact done by your network. So this all stuff related to visualization was actually meant to tell you how these techniques will in fact build towards the concept of neural style transfer. So that is why we discussed what it was today. Some part is left, and I will give you a video link where you can actually listen to them and understand a bit more. And the practical usability about these things is that so you have some filters in Instagram where you take a photo and they will automatically change the style of the photos to reflect what you want. So this is the concept which is actually going behind those things. And then there are some other applications where you can in fact substitute people in a video with another people. So that is the second sort of things which you want. Uh, yeah, so you might not have been able to understand the paper, and in fact I don't know because I haven't read this paper. So what you can do is you can send your doubts to Nidhi ma'am on me via mail, and I can have a link at that paper and I can revert back with the answers. But that is not the place for it right now because we are only talking about basics, not about the advanced things. Yeah, so after the lecture, since I am already working, uh, you can send it to Nidhi ma'am and she can send the doubts to me because sometimes many people are reaching out with the same doubts. So that way I can filter out and I can reply back to you. So, yeah. Any other doubt related to what we have covered? You guys can run these notebooks related to neural style and network visualizations, and you will be able to understand what I'm talking about. My PPTs and notebooks have already been shared with you. So it's now up to you whether we should proceed or do you want to wrap up? Means I have done with the saliency map from my end. I have to discuss three more topics which are related to generative fooling and this neural style. So from my end, the content is there, but it's your call then because you have another session. I think around 2:30, and you will have to go for lunch break also. Nidhi ma'am, could you please help me? Like, what should I do? Okay. अभी तो only Mostafa sir has said. Okay. So yeah, yeah. So till what time can I use? Okay. That yeah, yeah. That is why I am asking beforehand. How much time should I use? Because my content won't be over. Uh, you just tell me how much time, and I will trim the rest of the lecture accordingly. Okay, ma'am. Okay. Okay. Then. I can discuss two more things till that, and in fact, yeah. So let's move on towards hacking. So what I want is to hack a neural network. I'm done with improving the networks and I want to actually go ahead and hack the things because I am a person who wants to steal other people's data and I want to fool the places wherever decisions are taking place. So the idea is something like this that what I want is basically just a moment. Where is it gone? Before this. Yeah. So this is sort of hacking which I want to do, which is that on the first column, what you see is a person which is African elephant. Okay, I have one image which is looking like an African elephant. And what I want to do is then apply some magic to this image, which can actually change its category to koala. So what you see on the left is a person who is just yeah, what you see on the left is something which is like a African elephant. Everyone knows this is an elephant. So I want to do some sort of magic to this which can change the class a network thinks that it is. So it's like he thinks now that in the second column he thinks that this is a panda, a koala bear. So but when you look at these two images in front of you, you know that it is that the network is wrong, because these both things are looking like an elephant. But you went ahead and you did some magic on African elephant's image, and you got a network to actually talk about that it's a koala bear. So there must be some mechanism by which I was able to add these random perturbations to the input image, and I actually need to answer, because these sort of things actually raise a concern for us, that you cannot rely on a network to actually predict that the way a network predicts an image isn't right now entirely understood by us, because uh, two similar looking images can in fact give you two separate types of predictions in the networks. So uh, the best way to answer these sort of things is to actually do two parts. First, we want to understand how we can do some sort of processing in African elephant image and create this image where the network actually mistook it for the koala bear. And secondly, what we want to understand is that what is going on inside the network. So I will take the differences between these two elephants. One was the correct elephant, and one was where the network mistook it for a classification part. If that error, if I compute the error between them, then my intuition is that by computing the error between these two images, I can understand that okay, that maybe some sort of thing had happened. So uh, that is also what is not going on. If I take the error between these two images, then the difference appears to be almost zero. And in fact, the difference only becomes more legible when you zoom in into it and really start seeing some random noise. So that is why the this concept that you can take an image and you can transform it such that the new image only, it doesn't have much difference with the initial image, and you can still fool a classifier, is really a cause for our concern, because these days the neural networks are actually being used to create to perform decisions, and in case two similar looking samples yield to different decisions, then this can be very devastating. So maybe you have a neural network which talks about whether a aeroplane should be landing or whether it should explode in the air. Maybe you are carrying a warhead, and it should not explode in the air but only when it's hitting the enemy target, and a neural network is making these predictions based on the satellite imagery. And this is a sort of binary classification problem, and if it takes that sorts of different things and detonates at the wrong places, then it can be catastrophic for us. We are going to look at the first part, that how can we actually use a neural network to create these images like African elephant being mistook for the koala bear. So our aim today is to actually construct the images which can actually look like a koala bear. So that is what I am talking about. So the algorithm is simple, that you take the image. So you take this elephant image and you talk about what is the what is the image which you are trying to actually predict. So what I want is to create an image which can actually fool the network into thinking that it is a koala bear. So I will start with a random image, and I will start with the African elephant guy. I will pass the African elephant through the network, and I will get some sort of feature vector for the elephant, and I will pass, and then I will take the random. I will take a random image, and I will also pass it through the network and get some new feature vector. So it's logical that the difference between this new feature vector and this old feature vector should be almost same. And then there is another constraint that the score of this new prediction on the koala bears should be minimized. So if I actually train a network taking these two constraints into account, then in fact I can get something which is looking like this elephant. So what I will do is I will write the algorithm on my own, and then we will see that how it is being implemented. So I am going to write some stuff which is like very basic, and you will be able to understand it because you have already learned how we computed the saliency feature map. So let's look at slide 6. So it's like this, that what I wanted, what I had with me was an elephant, and what I want to do is make a new image which can in fact fool my classifier into thinking that it is a koala bear. So what I will do is I will pass this elephant through my network, and I will get a scores which contain its confidence on different classes. So I will what I will do is, and in fact I will get some feature vectors which represent this elephant. So what I will do is I will take the feature vector of elephant out of it. Okay, and similarly I will pass my koala bear through another convolutional, through the same convolutional network, and I will get the feature vector of koala bear out of it. So what I want in my loss is basically the Euclidean norm of my koala bear and the feature vector of my elephant to be minimized. And so this is like, it will tell that the new image which you construct should look like the elephant because you are taking the Euclidean distance between these two features. But I have not told this loss that what I want is to perform better on the koala bear class. So what I will do is, in fact, I will write a loss which can help me to classify it better in the koala bear class. So it can be maybe like score of koala minus score of elephant. And then what I want is that I want to apply some sort of regularization to my network, which is like lambda times f of noise pixels, right? And this is a regularizer function which I will go ahead and apply. So there is like one part which is telling the network that your image should look like the elephant, and then there is another part which is talking about that the score of the koala bear for the noise image should be maximized, and then there is a third part which is actually regularizing the pixel values which we are learning for our noisy image. So a loss function is containing three parts. One is the realism governed by Euclidean distance. The another constraint is that its score on koala should be maximized, and then the third part is that it should be regularized and it should not actually be overfitting. So if I take these three things in form of a loss, and I start with a noisy image, and I apply the gradient descent on individual image pixels, then in fact I can get a new image which looks like this elephant guy, right? And if I have it will look like this second column in this figure. And in fact, if I remove this Euclidean distance which tells it should not be similar to elephant, then it will just start with a noisy image and it will adjust that noise such that its score on koala bear becomes more than that of elephant. Then what you will end up is with this difference which does not look like an elephant at all, but in fact the network will think that it is a koala bear. So by adding a realism term to the loss, you can make it look like an elephant, and by adding the image of by removing this constraint, you can just guide a noise to actually perform like it is an elephant in real life. So it's the same idea as that of CNNS map, that you started with the image, passed it through the network, computed the deviation of scores, got back, and then computed a gradient map, took the max across dimensions, and got a attention map. So the same idea can be used, in fact, to actually create the images to fool a classifier. But the change is in the loss. We are adding two more terms to it. Uh, One is the classification term, that the score on the the koala bear class should be maximized, and the other one is the Euclidean norm, which is actually enforcing the constraint that the thing should look like the elephant in the final way. So this is the basic concept actually, and it's just two lines of implementation, nothing more. So what I went is that yeah, so I created a new image called X-fooling. So X-fooling was the same as the input image, and now I have to actually perform the back propagation on this image's pixel through the laws which I wrote here. So uh, it is like I am going through particular number of iterations, and I am passing my fooling image to get a score, and I know what my correct score for the koala bear class is going to be, and then I'm going to actually pick up the scores from that class, and I'm going to compute this distance between the classes, and then as soon as my system starts to actually generate its confidence to be greater than the koala bear, then I am done. So it's like when I was passing the elephant's image initially, I got an accuracy that it's 80% elephant. So if I'm able to make the network think that it's 80% koala bear, then I am done. So this is the part which does that you are looking at what is the fooling thing which you are trying to do. The target why is that I want the network to generate an image corresponding to koala, and then you are taking your scores which you are actually predicting for your fooling image, and in case your fooling image is actually able to predict whether the noisy image is koala or not, then you are breaking, because you don't order to no longer need to actually perform gradient descent on this loss anytime. And otherwise what is happening is that you are just taking the you are just computing the score. So you will pass a noisy image and you will find that it's koala bear score, and you want its koala bear score to be actually maximized, and that is why you are taking that koala bear score, and in fact you are then coming back and performing gradient descent. So in short, take a noisy image, pass it to the network, compute its score on koala bear, and then perform back propagation until the score of the koala bear actually becomes greater than the score of the original image on the elephant class. And once you get that image, finally you take a difference between these two images, and you will be able to find the image. So here I went ahead and I took on the left, I took a dog image which was originally classified as a border terrier, which is a breed of a dog. And I performed took this image as initial image and then performed gradient descent on it until the network's classification score got boosted on the hen thing. And then this was the image which we got finally, but still the network thinks that this is a hen, and when you actually take the difference between these two, you find out that it is nothing. So this is the way you are able to generate different images. You are able to guide a same single image to actually go and fool the network into thinking that it belongs to multiple classes. And when you look at the differences, there is a marginal difference between the pixel values. So this is a cause of concern for us. And as scientists, actually, what we need is a way to understand what is going on behind the scenes. So that is why the topic of adversarial learning is still undergoing a lot of research. So you people can go ahead and read some stuff on ICLR and ICML, which talks about like what is going behind the scenes in these sort of fooling mechanisms inside the networks. So yeah, I am done with the second topic with 10 minutes remaining, and I will take your doubts, and then we can conclude and wrap up. So if you have any doubts, you can unmute and let me know. related to actually fooling the generating fooling images for a network. Okay, okay. Yeah, anyone else? Is so I am going to wrap it up now, and if you have any doubts, you can talk here, and I'm waiting, and then otherwise we can proceed. We can just wrap up for the day. You have all the other. I will share the slides and all those things with you. So okay, Nidhi ma'am, can you please come online? Yeah. So, what do you increase? What are you meaning by increasing the fake image? Are you talking about increasing the fake images during training? That is the question which we are still trying to answer. That what is going on inside a network? That whether that it is able to actually learn something even if it is not perceptually visible to us. So I think that the answer lies in the way we are pre-processing the things. So what you do is perform a simple experiment, which I did. Take an image, apply normal standard deviation and mean to it, okay, and then just visualize that image. That will look like nothing to you, but a network is still able to use that image to perform classification. So I think that if we go into that area, that how is that simple transformation still being able to accurately be modeled by a convolutional layer. I think if we find that reason, then we can answer the question of why adversarial samples are working. And as to the question, if majority of your samples are adversarial, you won't be able to do anything out of it, because you want to look at real images and classify them. You don't want to look at fake images and do something. The best you can do is create a lot of these fake images and then generate a new fake image. So maybe you can make a generative model out of many fake images and learn to create more fake images out of it, and then gather all these things and then start hacking the system in form of a brute force. Give it an image until it cracks. So it is like adversarial setting where there is a generator at one end which is generating fake images, and then there is a neural network at another time where you will send these fake images until the network gets fooled. So it's a sort of brute force attack which you can design. Yeah, yeah. Anyone else? So we are wrapping up for the day, and we are having around 5 minutes. So we you can ping your doubts or ask it anything related to I have covered or not covered. Because the things I came prepared with and the things I actually covered, there is a lot of difference. So I am giving that stuff to you, and if you have any doubts, you can tell it to me right now. Okay. So I don't think anyone has any doubts. So, ma'am, I am handing the mic back to you. Thank you. Okay. Okay. Uh, just a minute. Yeah. Who is it? Yeah. So, do you want practical books or do you want theoretical books? Uh, do you want to know how to train models and work in industry, or do you want to know how things work and you are in a research or academia? I can give you the. I will tell you for that only, right? Okay, you want both the theoretical books. So for theory of neural networks, like Partha sir told, there is currently no good book in deep learning. Uh, I so people generally recommend Aaron Conville's and this Goodfellow's deep learning book by MIT Press for deep learning, but I think that is not so good. I generally read older research papers by Geoffrey Hinton's, and those papers are hosted on the Toronto's website, and I can show it to you. You can go to just Google Hinton and then go to this guy's website, and here you will find publications by year thing. So start reading from the reverse end. So start reading from the 1976 papers if you want to know some good things. And Capsule Nets is working right now at Google, so that is not worth reading. Yeah, so for learning how neural networks work function theoretically, you can start reading these papers, and then he is hosting some other stuff which is talking about lectures of neural points from a brain point of view. So uh, right now what we discussed was how they function mathematically. Didn't discuss intuition. So you can look at these lectures for building your stuff about their brain analogies. So this was in older times. Now this course was taken off Coursera, and for the so this is related to the theoretical part. For the practical part, there is two things which I generally refer to. One is Sumit Chintala. So Sumit Chintala is has been working in PyTorch, and then you can go ahead and look at his tutorials. Yeah, so this is like the basic stuff which has been written by Sumit Chintala, and then there has been a book on PyTorch by Sumit Chintala. His advisor had been, I think, Bengio at this NYU. So you can look at this book, Deep Learning with PyTorch, which is by Ellie Stevens, uh, talking about how to use PyTorch for training models. This is the practical part. And then there is one other book on practical deep learning by Jeremy Howard from Fast AI. Yeah, practical deep learning. Sorry. Let, let me look up that book. Yeah, this one, Deep Learning for Coders with Fast AI and PyTorch. So two books you can see. One is Deep Learning with PyTorch by Sumit Chintala. He wrote the foreword, and then there is another book, Deep Learning for Coders with Fast AI and PyTorch, and their code is available for free on the internet. So these are the practical books. Uh, Anyone else who needs some recommendations about material or anything else, if you want, any problems you face in general deep learning and something like that. Okay, yeah, Nidhi ma'am, I think we can wrap up now. Okay, and the online tutorial course you recommend. Okay, my again question to you is: are you a person in industry or are you a person in research? Uh, what do you need for that? So, okay, I will talk. Okay, you only want from industry perspective. So then in that case, don't go anywhere, just go to this website, deeplearning.ai. They are running all the courses which are hosted on Coursera. Choose what you want and start reading from there. So they have these courses. All these courses are good. You can choose any one of them, and you can go to Coursera and learn about those. So whatever field you want, start from there, particularly related to neural networks. Okay, for research, okay, okay. Manan needs for research. What are you looking for in research? Any particular topic or? anything related to something else like CNN or something. Genomics, sorry, I don't have any idea because I don't have a computational biology background. No, sir. Financial engineering, I can't tell. I can tell you feature engineering and the data stuff related to normal data science, but not for that. So, for finance, you can have a look at this guy. Financial engineering, you can have a look at this course. Intro to, yeah, sorry, Fast AI course V3 2018. Intro to ML, Jeremy Howard. So this is the stuff where I prepared the random forest lectures. So will give you tips related to the data science part, and you can actually because in finance, my understanding is you have tabular data, so you can use your data science skills there, and then yeah, for natural language processing, in case you are doing the theoretical, in case you are doing practical part, then you can refer to the deep learning.ai's thing, uh, which contains a natural language processing course. uh, deep learn sorry Yeah, so deep learning.ai, it contains this course related to natural language processing, but this is not only good if you are in industry. In case you want a bit more thing, then you can go to Christopher Manning's course. Christopher Manning, uh, I don't remember the code, but Stanford is actually hosting a course which is related to neural NLP language. Yeah, Stanford NLP. No, no, no. Go to YouTube and there you will see. Uh, just a minute. Yeah, Chris Manning, NLP. Yeah, so you can have a look at these CS224N. You can have a look at these courses, which are good. And anyone else need for data science, I have told you can look at Jeremy Howard's Intro to ML, and for NLP, I have told you the Deep Learning AI and CS224N. Yeah. Okay. So, any other recommendations you need for anything else like uh, something else related to ML or like that? Okay, then. Thank you very much, and it has been my privilege to listen to teach you guys for these 3 days, and I hope that I get a chance to come again and teach some of what I have known and learn from even you people. So I'm sorry I was not able to come at Hamirpur this time. So let's see if I can come any day and I will check. Yeah, yeah. Okay, thank you. Yeah, ma'am.